Okay, so let me start. So the topic for my lectures is Chern classes of vector bundles. So before we actually start with Fulton, the first lecture is going to be about Chern classes in the topological setting. So we will, so the reference for the first lecture is this book by Alan Hatcher. So this is called Vector Bundles and K-Theory. And all I am interested is on only one theorem in this book, so that is theorem 3.2. So in case there are some missing gaps, if something is not clear in the lecture, you can go and look up for details. So this is the reference. This book is freely downloadable. There are two reasons why I want to first do this topological Chern classes or Chern classes for vector bundles on topological spaces first before going to schemes. One is that we still need time to develop Chow groups and get used to that, and there is great danger of losing sight of main ideas in that technicality. So we will first, this will give us the main idea. And the other reason is that the ideas in the proof that we will see, they actually can be just directly implemented there, most of the ideas. In fact, this proof was first written in algebraic geometry and then transferred here. So, okay, so let us begin. So let X be a topological space. And so recall that a complex vector bundle of rank n on X is a space E with a map to X. Let's call this map pi. So it's a topological space E with maps to X, and the fibers are complex vector spaces. That is the general idea, but a little bit more than that. So we say that this vector bundle is trivial on an open cover of X. So there exists an open cover such that there exists an open cover X, let's say union of U alphas, such that if I restrict this vector bundle to U alpha, which means I take the inverse image of U alpha in this E via this map pi, so such that pi inverse of U alpha, this is isomorphic to U alpha cross Cn. Okay, so and the isomorphism is over U alpha or over X if you want. Okay. So this is so we have such isomorphisms. Let's name these isomorphisms as F alpha. And there is one more condition, that if I look at F beta inverse, okay, one more condition. So F beta inverse composed with F alpha. This is a map from U alpha intersection U beta cross C to the power n to itself. This map is given by, this map is linear on fiber. So basically there is a matrix of n cross n matrix of functions on U alpha intersection U beta. So this which defines this map. So this is given by GLN U alpha intersection U beta. Okay, so let me just say something more about that notation. So OX will denote the sheaf of continuous complex valued functions on X. Okay, so this is what a vector bundle is, and something that we need later on, but not right now. Maybe in discussion session we can discuss this. So there is an isomorphism, equivalence of categories. So vector bundles are the same as, let's say, vector bundles of rank n are the same as locally free sheaves, locally free OX modules of rank n. Okay, we don't need this statement, but how many of you know this? Okay, excellent. So then even though we don't need this, in the next lecture this will be useful, because we will talk about line bundles as mainly sheaves rather than this topological way of thinking about. Okay, so what is theorem 3.2? This entire lecture is about 3.2. So, yes. Co-cycle condition. No, so there is no co-cycle condition needed, because I start with a space on X. If I want to start with vector bundles on U alpha and then I have to patch them, then I need co-cycle condition. Yeah. Yes.
That doesn't come out of this.
No, because the
one open source are compatible.
Yeah. So yes. So just to be so let me add this. So there is a map and a C linear structure such that so basically it means that I have addition at the level of E. So E cross E over X to E, I have addition, and I have scalar multiplication by functions on X. Okay, so which is preserved by this. Okay, so let us so that vector. So this is the condition of local triviality. Then maybe once I say this, I need not say that if it's preserved by this, then automatically then I don't have to say that, I think.
The best way would be to say from E power to E.
Yeah. Yeah. So let me add that in the definition. So E, so there is a complex structure on E, which means E fiber product E over X to E. There is a map as X spaces, which basically satisfies the axioms of and there is a scalar multiplication. So C, or rather, yeah, okay, C cross E to E. Oh, yeah. So C cross E over X. Yeah. This over X. So this gives the so this satisfies the axioms similar to axioms of a vector space, and this isomorphism this preserves that structure. It is I still think that this actually gives, but let me just maybe in the maybe I'm wrong. So let us see what theorem 3.2 is. So so 3.2 is the numbering of the book. Okay, so there exists unique functions C1, C2 and so on, indexed by natural numbers. Okay, so C1 Cn for every natural number n, okay, which assign to every complex vector bundle, okay, so every complex vector bundle E over X classes, so Ci takes this vector bundle and assigns an element in H to Y of X Z. So this is singular cohomology of X with coefficients in Z. Okay, so the such that so first is that there is a so this assignment is functorial, so which means okay, so for since you have seen the vector bundles already, I am assuming that you are familiar with pullback of vector bundles. So if I have a map, continuous map from Y to X, I can pull back the fiber product of E cross Y over X is a vector bundle on Y. So that is actually straightforward to check. So this is well behaved with respect to pullbacks or it is functorial. So which means Ci of F upper star E. If I pull back a vector bundle, let's say for F, a continuous map from F from Y to X, Ci of F upper star E, and E is a vector bundle on X. This is the same as pullback of Ci of E. This Ci of E is called the ith Chern class. Okay, so we have to show that they exist and first see what properties are satisfied by that, and then show that there are unique classes which satisfy these properties. So there is this is the pullback map defined on singular cohomology. Okay, so second property that we want is that yeah, so maybe there is a zeroth property also, that Ci of E depends only on the isomorphism class of E. So Ci of E depends only on the isomorphism class of E. So if two vector bundles are isomorphic, their Chern classes are going to be the same. Second property tells us what happens to direct sum of vector bundles. So C of E, 1 direct sum E2 is equal to C of E1 cup product with, or I can just use multiplication for cup product, C1 dot C of E1 dot C of E2, where what is C? There is no suffix for C, where C of E, maybe this is too small, right here. C of E is 1 plus C1 of E plus C2 of E and so on. This is an element of the cohomology ring. Take direct sum of all the cohomology groups of X, and this total Chern class, this is called total Chern class. Here? No. I'm going to state it as the fourth. Yeah. So even if it does not, the product will still make sense because in the direct product. Yeah. Okay. Yes. So let me comment that after I write down the property. So this is called the total Chern class of E. I just take the sum of all Chern classes. The problem is it is not living in any one cohomology group, but the whole cohomology ring. So as Nitin pointed out, this actually appears to live in the product, but the next axiom says actually it is in the direct sum. So it's actually in the cohomology ring. So maybe the order should have been to state this first. So Ci of E is equal to 0 for all I greater than the rank of E. if the rank of the vector bundle is n, then it can at most have non-zero Chern classes up to n, C1, C2 up to Cn. All the further Chern classes are 0. Okay, so now there is obviously one set of such functions which satisfy all these properties. Can you guess? Yeah, of course, 0. So somewhere there has to be some condition which will ensure that something is non-trivial. So this fourth condition says that if O minus 1 is the universal, what is it called, universal or canonical? Tautological, sorry, is the tautological bundle, tautological line bundle just means vector bundle of rank 1. Okay, so line bundle on P1 of C. Okay, P1 of C here considered as a topological space. So if I take the tautological line bundle on P1 of C, then C1 of O minus 1 is a generator of H2 P1C specified in advance. So this is written in a slightly roundabout way, so I'll just let me comment on that in a minute. So specified in advance. Okay, what does this mean? So first of all, what is the cohomology? What are the cohomology groups of complex projective space of P1C? Yeah, 0 and H2 is Z. What about H1? We don't care, but it is 0. So actually the theorem maybe could have been stated that choose, so this is isomorphic to Z. Okay, so this is isomorphic to Z, so you can choose one of the two generators of this. So what we are saying is choose that generator. Once you choose that generator, there is a unique way of assigning Chern classes to vector bundles satisfying all these conditions, and such that Chern class of this O minus 1 is your chosen generator. Okay, so this gets rid of the non-triviality, and not just that, we are saying that there is so I want to emphasize this word unique. There is we will discuss one construction, but no matter what construction you use, if it satisfies these properties, there is basically a unique way of defining Chern classes. What we will do is, first we will define Chern classes of line bundles. So that is the step, and in fact when we start doing it for schemes and varieties, this is also the first step. So first we will do define Chern classes of line bundles. So in fact let us prove uniqueness first. So let us first show uniqueness. So why is this set of these set of functions, why do they have to be unique once I write down these properties? So there are two ingredients in proving this uniqueness. So first is that if I look at P infinity C, so this is the union of all projective spaces. Right now it is just topological space, so I am not considering this as varieties or anything. So take the union of all P and C n greater or equal to 0. When I say union, of course I am making a choice of the embedding of Pn inside Pn plus 1. Okay, so this is the classifying space for line bundles. What does it mean, classifying space? It means that, so that is for any topological space X, homotopy classes of maps from X to P infinity C. Okay, so this is the notation for homotopy classes of maps or maps up to homotopy. Okay, so this is isomorphic or in natural bijection with isomorphism classes of line bundles. So line bundles on X up to isomorphism. Okay, so there paracompact, yeah, so for nice topological spaces. Okay, I can just say CW complexes or yeah, so nice, let me just use nice. Okay, so paracompact Hausdorff or take, it doesn't have to be a manifold. Okay, so not so nice. So so giving a line bundle is the same as giving maps to this space, infinite projective space. So it's one way is easy to see. If I give a map from X to the infinite projective space, how do I get a line bundle on X? Pull back O minus 1, right? So that is clear. You'll have to do some more work to show that this is actually a bijection, and yeah, so this is ingredient number 1, okay, in showing uniqueness. What is ingredient number 2? Unfortunately, this ingredient number 1 will not be available in algebraic geometry. We'll have to do something else. But ingredient number 2, as it is exactly verbatim, we will have in the algebraic geometric setting. This is called a splitting principle. Okay. So what this says is the following. So it's called principle, but it's actually a theorem. So if E is a vector bundle on X, E is a complex vector bundle on X. Okay. Then there exists a map F, continuous map F from Y to X, such that first this E, when I pull back E, it becomes direct sum of line bundles. Okay, so F pullback of E is direct sum of Li, where Li are line bundles. Of course, there will be rank E many line bundles. Secondly, if I look at the map induced by F on the cohomology ring, so F from the cohomology ring of X to the cohomology ring of Y, this is injective. This is injective. So what this splitting principle or what this result, we will, so I'll comment on why such a space Y exists in a minute. But what this allows us to do is, if I want to check some calculation, let's say we want to check uniqueness, for example, I can go to a space without losing information because this map is injective. There I can check equality of cohomology classes. I can go to some other space where this E becomes direct sum of line bundles. Okay, so that is the idea. So what we will do is, first let us observe that uniqueness holds once I have these two ingredients, and then I'll comment about this. Yeah, so what are the choices for Chern classes of line bundles? So the splitting principle tells me that once I have Chern classes of line bundles, and I know that how Chern classes behave for direct sums, everything else will be determined. So the question is really whether Chern classes for line bundles are determined. So if L is a line bundle on X, L is a line bundle on X, then because of that that first result, that P infinity C is a classifying space, there exists a map F from X to P infinity C such that pullback of O minus 1, this tautological bundle, is isomorphic to L. Okay. Now, this theorem through 3.2 tells me that the first Chern class, so a line bundle will only have one non-trivial Chern class, namely the first Chern class. All other higher Chern classes will be 0. Okay. So, I know that the first Chern class has to be the pullback of the first Chern class of O minus 1 on P infinity C, right? So therefore, C1 of L is, this has to be equal to pullback of C1 of O minus 1. Okay. But what is C1 of O minus 1? We know that C1 of O minus 1 on P1 is already chosen. But you see, if I look at the map from P1 C to P infinity C, the inclusion, then O minus 1 on P infinity C, this pulls back to O minus 1 on P1, right? And the cohomology group H2 of P1 C, now coefficients will always be Z, so let me suppress them. So this is isomorphic to H2 of P infinity C. The second cohomology group is isomorphic. So therefore, the Chern class of this is determined by what is the Chern class of the pullback to P1C, which is our chosen generator of H2 P1C. So there is a natural. So therefore, this Chern class is of course determined, or I could have just said that Chern class of O minus 1 on P infinity C is the chosen generator of H2 of P infinity. So yes, yeah, I'm going to reverse that. So this shows us that splitting principle and this the fact that P infinity C is a classifying space gives us uniqueness in the theorem that we want. So this proves the uniqueness part of 3 point. Okay. So is it clear how uniqueness follows? Because for all line bundles I have the first Chern class. Once I have it for line bundles, for any other vector bundle, whatever its Chern class, it has to agree with the product of its total Chern class has to agree with the product of total Chern class of the line bundles after pullback to Y, whatever Y exists because of splitting principle. But this map is injective, so once they agree after going to Y, they have to agree. So uniqueness is clear, right? So let me know if okay. So your uniqueness is clear. But what about existence now? So how do we show that such a thing exists and satisfying the required properties? Even before existence, let me say something about the splitting principle. Okay, so the splitting principle, so what is this space Y? So it can be constructed as a flag variety, but I think it's easier to see it as a successive projective bundles. That is maybe easier. So I'm going to so there are of course more than one choices there. So let us observe the following. So this is a theorem that we will not prove in topology, but in algebraic geometry we will prove it. So this theorem says that if E over X is a projective bundle, is a vector bundle, and P of E. So this is the projectivization of this vector bundle. So this is the projectivization. Yeah, what does projectivization mean? So for a vector space, the projective space associated to a vector space is the set of all lines given with appropriate topology. What about a vector bundle? Same thing you do fiber wise. So since it is locally trivial, you can also do it on an open set. This maybe is a topic for discussion session. Unless it's very clear, then there is no need. So let P of E be a projectivization of E, and what this theorem says is that the cohomology of P. So if I look at so the cohomology of actually, before even I state this, let us first write down the cohomology of projective space. So you see H star of P and C. If I just look at projective space and projectivization of a vector bundle, the fibers are going to be n-dimensional n-1 dimensional projective spaces if this is of rank n. So H star of P and C, this is actually alternating. So all the even cohomology groups are Z and all the odd ones are 0, right? Up to 2n, and beyond 2n they are 0. So this is yeah. So this is Z direct sum 0 direct sum Z and so on up to 2n, which is. But what is the cohomology ring structure? So as a ring, maybe let me write down the ring structure. As a ring, this is isomorphic to Zx modulo x to the power n. Okay, so for an element n plus 1, yes, for an element x in H2 of P and Z. Okay, so for a generator X of H2 of P and Z. So this is the cohomology ring structure. Now what this theorem says, this is a theorem about calculation of cohomology of projective bundle. This says that for any class, so let me, yeah, so for any X in H star of, or H2 of this projectivization such that X restricts to a generator of the fibers H2, so which means if I look at H2 of P of E and its fiber at a point X, this is an n-1 dimensional projective space, and it's so X, if it restricts to a generator of this, then this cohomology ring H star of PE, this is of free H star X module with basis 1x up to x to the power n minus, okay, let me fix a rank, so vector bundle of rank n. Okay, this is vector bundle of rank n now, so therefore this projectivization has fibers which are n-1 dimensional projective spaces. So now if I look at 1x up to x to the power n minus 1, then these are the free bases for the cohomology ring of P of E as a module over H star of X. So that is the theorem. Okay, so this we will see a proof of this in algebraic geometry, where of course the cohomology ring will be replaced by Chow groups. So this gives us actually this actually shows, this proves the splitting principle once we have such a calculation, and the idea to prove the splitting principle will be the same when we start discussing Chern classes in the algebraic geometric setting. So why does this prove? Because
We are not said why X exists.
huh?
We are not said why X exists.
Oh, I have not said why X exists. Yes, I have not said why X exists. So yeah, so for example, X equal to the first Chern class of O minus 1. Okay. Now let me comment on that. Okay, so satisfies this condition. So this works. So let us look at, yeah, so this needs maybe more discussion. So let us look at this projectivization. So
There existed for any x.
For any x, but there exists such an x is what we have not said.
oh, my point is also x. Sorry. This is p. Was that the confusion? No.
For any x.
For any class which restricts to generators at every fiber. So I have to first show, so his comment was that I have to first show there exists at least one class which restricts to generators on every fiber, right? Generator of H2 of every fiber. Okay. So first we have to see this. And secondly, no, I think this is enough. So this is all we have to show. No, I changed that point. My point was also x. That became p now. Yeah. So yeah. So why does there exist? First of all, why does there exist a class which restricts to generator of H2 of every fiber? Okay. So I am giving you that class. So let x equal to C1 of O minus 1. Now we already know what are Chern classes of line bundles. Because Chern class of P of the tautological line bundle is the generator, and for any other x, I am just going to define Chern classes as pullback. So Chern classes of line bundles are already defined, right? So or what this means is take the map, classifying map from this P of E to P infinity C, such that the pullback of this tautological bundle is the pullback of that of the tautological bundle on P infinity C, and that is my class x. Now x restricted to any fiber, let's say P E P. So what is the fiber? The fiber is isomorphic to a projective space, and it is a simple exercise to see that the tautological line bundle of the projectivized bundle restricts to tautological line bundle on fiber wise. Okay. So therefore the Chern class of this O minus 1 of PE, okay, so this is Chern class of tautological line bundle of the projectivized bundle. This restricts to the Chern class of the tautological line bundle of the fibers. So this is isomorphic to C1 of O PEP. So now this is a projective space minus 1. But by our assumption, this is the generator of H2. So for any projective space, the first Chern class was the generator of H2. So therefore, there exists such a class. Maybe I could have directly said that for the first Chern class, this is a free module. So that is maybe, but because we are still defining Chern classes, therefore I stated this theorem in this fashion. Okay, so therefore there exists such a class, and this theorem we will assume that this is a free module. Now this shows the splitting principle. Why? Because on P of E, okay, the tautological line bundle is a sub bundle of E, of the pullback of E. Sorry. When I pull back E to P of E, the tautological line bundle is a sub bundle of that. So is this? So I'm expecting some question if it is not clear. My claim is that the tautological line bundle is a sub bundle of the pullback of E, and this is probably not clear. So what is the tautological line bundle? So the tautological line bundle, you see, for every point it assigns the line which is parameterized. So every points of the projective spaces are lines. So let us look at what is happening at for projective space. So if there is something you want to understand for projectivized bundles, the first thing to check is what is happening for projective spaces. Okay, so let's say V is a vector space. Okay, so instead of taking Pn, I am going to talk about P of V. Okay, so then let P of V be the projective
Pi is the maximum P of P2.
Pi is the map from E to X, yes. Then is it clear?
Pi of but then X is going itself maximum.
Now this will also come now by the PE person X, so now that we will.
Oh yeah, pi is also the map from PE to X. This I'm not giving a name. This is the name pi. Yes. Yeah. Then is it clear? Okay. Let us go through this. So if V is a vector space, then look at projectivization of V. Okay. So this is the projective space of V. Okay. What is the tautological line bundle of this projective space? For every point of P of V, you assign a line, right? So I have to give a line bundle. So for every point I have to give a line. I have to give, so it is that line which is parameterized by that point, right? So for P in P of V, we have, so this corresponds to LP, which is a line V, right? So basically this, so then you can see that on P of V, inside P of V cross V, PV cross V, so this is the trivial vector bundle on PV. Here there is this tautological line bundle, right? And I just told you what are its fibers at every point. For every point P, this is P comma that line, right? This is the tautological line bundle, right? So similarly, now you do this for vector bundles on X. So V was a vector bundle on a point. Okay. Now we will have vector bundles on X. So similarly, if I look at PE cross E over X, this is my pullback. Inside here I have to give you this line bundle, which is the tautological bundle. So the main problem is maybe recalling the definition of the tautological bundle. So this is the sub bundle where so this maps to PE. So where what is its fiber over P? So if P is a point, small p is a point in PE, the fiber over this has to be, so this is fiber product over X. The fiber over this has to be a subset of EP, right? So this is that subset of EP. So so this point of so P corresponds to, or P corresponds to a line in EP, right? So projectivization of a vector bundle is projectivization of all the fibers. Fiber wise it is projectivization. So for every point P, if the fiber is this EP, then so then this, yeah, so P, if I have a point of, sorry, this has to be pi of P. Yeah. So a point of the projective space which lies over a point of X. What is that point of X? It's pi of P. So giving a point of a projectivized bundle is giving a point of the topological space and a line in its fiber. So that is what I am trying to say actually. So therefore this line actually gives me a subset in PE cross E. So let's say P corresponds to a line, I'm going to call it LP, and then I just take the subset P comma LP as P varies inside here, and this gives me a line bundle on PE. That is the tautological line bundle. So the tautological line bundle is actually constructed as a sub bundle of the pullback of E. Okay, so therefore I have this sub bundle, and the quotient is a vector bundle of smaller rank. So the quotient is a vector bundle of, so therefore we have a short exact sequence of vector bundles. O minus 1 pullback of E and whatever the quotient, so let me give it a name F. Okay. Now in topology it so happens that every short exact sequence of vector bundle splits, so therefore pi upper star of E is isomorphic to O minus 1 direct sum F. Okay. So therefore my vector bundle, if I pull it back to the projectivization of its own, so P of E, it becomes direct sum of a line bundle and a smaller rank vector bundle. And is the map on the cohomology ring injective? Yes, because in fact this cohomology is a free module over this and 1 is one of the bases. So therefore the pullback map is certainly injective. Now by induction I can assume the splitting principle for F, but in essence what we are doing is further taking projectivization of F. There F will become, the pullback of F will become line bundle direct sum something smaller until you end up with all line bundles. So this is the proof of splitting principle modulo the calculation of cohomology ring of projectivization of a bundle. Okay, so X modulo this, so this is something we have not proved, but assuming this, the rest is clear, right? So okay, yeah.
The final space that you want to obtain for this splitting principle is the topmost.
Yeah.
And for which so we will pull back each O minus ones. So
Yeah.
O minus ones that we will got by reducing the rank.
Yeah.
We will be pulling them back.
Yeah.
So will those be like, will the pullback of that still be O minus 1?
No. It may not be O minus. I just want my vector bundle to be direct sum of line bundles. Whatever the pullback of O minus 1 below, it is some line bundle. That is all. Of course, it will not be the O minus 1 of it. It's something pullback from below. Okay. So all we want in the splitting principle is that we want the vector bundle pullback to become direct sum of line bundles and the map on cohomology rings to be injective. Okay, so this proves uniqueness. Okay, so if there are any questions, then let me know, because I'll erase this and then we'll start. Then we'll talk about the construction. Okay, so
Just write down the word variation without further comment.
actually that is the best idea, Lire-Hirsch. So this is Lire-Hirsch theorem. Okay, so Lire-Hirsch. Okay, so construction now. So how does one construct classes which satisfy the required properties? So again we start with a vector bundle E over X. We already have defined Chern classes for line bundles. So now so we can assume that E is of rank greater or equal to 2. So let's look at the projectivization of X. So that actually restriction is not really required. So you can even for line bundle the same thing will work. So let P of E be the projectivization of E. Okay. Now we know that. So let X equal to the first Chern class of. So this map is pi of the pullback of. The first Chern class of O minus 1. This is a class in H2 of P of E. Now this Lire-Hirsch theorem says that 1x up to x to the power n minus 1 is a basis for this cohomology. So therefore x to the power n, so x to the power n, this class which is in H2n of P of E, this can be written as this is a linear combination. So this is a linear combination of 1x x square up to x to the power n minus 1, linear combination but with coefficients from the cohomology of the base. So with coefficients from h star of x, right? So that is what so that is the consequence of this being a free module over this. So let us write down this linear combination in the following way. So therefore there exists unique classes, and in anticipation I am going to call them as Ci of E. So such that x to the power n plus C1 E x to the power n minus 1 plus C2 of E x to the power n minus 2 plus dot 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 Cn of E is equal to 0. So in other words, whatever these coefficients after rewriting them in this form, so x is linear combination of something, take everything to the left hand side, these coefficients I am going to declare as the Chern classes of my vector bundle. So Ci are defined by the following equation basically. So such that, so this is the definition of Ci, the Chern classes. Now we have to prove the properties of this Chern classes. Is it clear, the definition? Okay, so now let us start proving the properties. So the fact that this depends only on the isomorphism class of E is straightforward. So some of these I am going to skip and leave it as an exercise, because if E is isomorphic to E prime, then P of E will be isomorphic to P prime. That isomorphism will preserve the tautological bundle and it will pull back this linear combination. So that is straightforward. So this is so 0 is okay. So 0 was the property that it depends only on the isomorphism classes. The first condition was that it is well behaved with respect to pullback. So Ci of f upper star E is equal to f upper star of Ci of E. Okay, this was the first requirement. This also I am going to do verbally, because you see, if I pull back a vector bundle, then the projectivization of the pullback and the pullback of the projectivization they agree, and the tautological glass also gets pulled back, and therefore this also is very straightforward, because what you will get is that such a relation, its pullback is 0. But anytime I write such a relation, these coefficients Ci have to be unique, because this h star of P is a free module over this with basis, so that line I erased, with basis 1x up to x to the power n minus 1. So therefore this x to the power n can be expressed uniquely as an expression like this. So anytime I have an expression like this, the coefficients have to be, they are uniquely determined, and that is my definition of Chern classes. So this is also straightforward. It is just seeing that projectivization and tautological bundle, they basically are well behaved with respect to pullback. So second, so this is where we have to do some work. So second, so C of E1 direct sum E2 is C of E1 times C of E2. Okay, the Chern classes are, so this we will prove. Okay, so this I am going to prove. Others I want to just hand wave. Okay, so or Ci of E is equal to 0 for all I greater than rank of E. That is almost by definition. So I define Cn plus 1 onwards to be 0. Okay, so that is the definition of this in this construction. So this is also okay. This is okay. What else was there? C1 of O minus 1 is that chosen generator. We started with that. So we only have to observe this, that C of E1 direct sum E2 is the product of the Chern classes of a direct sum. The total Chern class of the direct sum is the product of total Chern classes. So that is what we have to observe. So what we need now is to actually look at how the projectivization of E1, projectivization of E2, how they sit inside projectivization of E1 direct sum E2. So, we will show, so we need to show that C1 of E1, sorry, C of E1 direct sum E2, not just C1, is equal to C of E1 times C of E2. Let us prove this. So now let us look at projectivization of E1 direct sum E2. Okay. Inside this I have projectivization of E1, because projectivization of E1 direct sum E2 fiber wise, its points are lines of E1 direct sum E2, and projectivization of E1 for every fiber, its points are lines of fiber of E1 over that point, right? So therefore this inclusion is clear, and I also have P of E2 here. Okay. So now to observe what is exactly happening here, I want to first look at a similar situation just for projective spaces, which means instead of working over a base, let's see what happens over a point. So let's say rank of E1 is equal to n and rank of E2 is equal to m. Okay. So we are looking at one fiber. So the fiber will be isomorphic to P of n plus m. So the fiber of P of E1 direct sum E2. So I am looking at P of n plus m minus 1. And inside this I have a, so this is, so I have chosen basis for my vector space of the fiber. So this is the set of the points of this are represented by homogeneous coordinates x1 up to x n plus m. Okay. X0 up to x n plus m, sorry, x1 up to x n plus m, let me write it like this. So this is how I represent points of this, and inside this I have a copy of Pn and a copy of Pm, where I am looking at specific copies. So this copy of Pm is the set of all points which lie, so this I am viewing it as projectivization of Cn direct sum Cm. Okay, so maybe this is, and this is, sorry, this is P n minus 1 and m minus 1. So my dimensions were wrong. So projectivization of Cn, and here I am looking at projectivization of Cm. Okay, so I want to see how projectivization of Cn and projectivization of Cm sit inside the projectivization of the direct sum of Cn and Cm. So what is this, how is this copy sitting here? So this is the set of all points where the last m coordinates are 0, homogeneous coordinates are 0. So x1 up to xn and 0 0 0, right? And what is this? This is the set of points where the first n coordinates are 0. So this is 0 and then xn plus 1 up to xn, right? So the intersection of these two, what will be the intersection of these two subsets of or subspaces of Pn plus m minus 1? Intersection of this and this. It will be empty, because there is no point whose all homogeneous coordinates are 0. Okay, so that let us make that observation here. So P of E1 intersection P of E2 is empty. Okay, now I want to take the complement of this. So consider the map from P of Cn direct sum Cm minus P of Cn to P of Cm. Okay. What I'm doing is I'm just projecting the coordinates. So this is a projection map. So here I take a point with homogeneous coordinate x1 up to xn plus m, and I project it onto the last m coordinates. So this is I make the first 0 and xn plus 1 up to xn plus m. Of course, this map is not defined when all these last coordinates are 0, which means it is not defined for points which lie in this projectivization, right? And but outside this is well defined. What are the fibers of this map? So if I take a point here, what is the inverse image? Sorry? No, it will be actually Cn, not PCn, but actually Cn. Right, because I don't have the flexibility to scalar multiply this point, because the target coordinates are fixed. If I scalar multiply, I have to scalar multiply all points, right? So the fibers are all complex vector spaces. Okay, so in fact this is a vector bundle of rank n. But what we want is that this open set of this space deformation retracts to P of Cm, because all the fibers are vector spaces. I can actually have a continuous homotopy of the identity map where ending at the at this retract. So therefore, so in fact, let me write down the conclusion here. So if U1 is P of E1 direct sum E2 minus P of E1, then U1 deformation retracts to P of E2. Okay, then U1 deformation retracts. So basically P of E2 is contained in U1, and this inclusion is actually a homotopy equivalence. In fact, U1 deformation retracts to P of E2. No, what I'm doing is I'm writing down the argument for this setup, and I'm directly writing down the statement for projectivization. There I have to keep track of one more point of the base. That yes, I'm not claiming that. Every vector bundle deformation retracts to the space. It doesn't have to be a trivial vector bundle, right? Because I can just scalar multiply by 1, and 1 I can connect to 0, and then that gives me a homotopy which shrinks everything to the 0 section, right? So it doesn't have to be a trivial vector bundle, but it deformation retracts. So therefore the complement of P of E1 deformation retracts to P of E2, and similarly the complement of P of E2 deformation retracts to P of E1. So this is actually enough to give us the relation that we want. Let us see how. So let X be equal to the first Chern class of O minus 1 of this P of E1 direct sum E2. Okay. Now let us look at this this expression, x to the power n plus c1 of E1 x to the power n minus 1 plus all the way up to Cn of E1. So I am looking at the expression which is similar to the one used for defining Chern classes of E1. Okay, so let's look at this expression. This restricted to P of, what happens when I restrict this class? Now as it is, it's a class in the cohomology ring of P of E1 direct sum E2. What happens when I restrict it to the to P of E1? The point is tautological bundle of this projectivization will restrict to the tautological bundle of P of E1, and therefore this X will restrict to the corresponding class here, and therefore this was the this equal to 0 was the expression used for defining Chern classes. So therefore this restricted to P of E1 is 0, right? This restricted to P of E1 is 0, but P of E1 actually is a deformation retract of the complement of P of E2. So this, I can just say that this restricted to U2 is 0. U2 was the complement of U2 is the complement of P of E2. Right, so this because the deformation like up to homotopy, the cohomology of P of E1 and U2 are the same because U2 deformation retracts, and therefore if this restriction to P of E1 is 0, then restriction to U2, this open set will also be 0, right? That is clear. So similarly, if I look at x to the power m plus C1 of E2, x to the power m minus 1 plus dot 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 Cm of E2, this restricted to U1 is 0. Now what happens to the product? So now therefore if I multiply these, so these are cohomology classes in the ring, they are restricted, they are 0 on U1 and U2 respectively. What happens to the product? The product I claim is 0 on U1 union U2, which is the whole space. So therefore x to the power n plus dot 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 Cn of E1 dot product with x to the power m plus Cm of E2 is 0. That is the claim. And the way to see this is using relative homology. So so this restricted to U2 is 0, therefore this lifts. So there is a map from H star of, let me use the word just symbol P for P of E1 direct sum E2. If I look at cohomology of P relative to U2, this maps to cohomology of P, and the fact that this cohomology class restricted to U2 is 0 means that this class, whatever this class is, this, let us give this name. So this is alpha. Before restricting, this class is alpha, and before restricting, this class is beta. Okay, so alpha actually lifts to a map in this relative cohomology group, and similarly beta lifts to a map in this relative cohomology group H star of P of U1. Okay, let's call this beta tilde, and so this cup product of these two, actually it lands in H star of P U1 union U2. Okay, the way cup product is defined, and it is compatible with respect to this map from relative cohomology to absolute cohomology. So we have such a diagram. So I claim that alpha times beta is 0 because this group is 0 now, because U1 union U2 is actually the whole space. So therefore this relative cohomology is 0, and therefore this alpha times beta is 0. This gives me some relation that the ith Chern class of E1 direct sum E2 is equal to summation over R plus S equal to I CR of E1 times CS of E2. Okay, because once I have an expression which says x to the power n plus 1 is linear combination of lower x's, that is the defining relation for Chern classes, and therefore if I expand this, I get these as the coefficients, but they have to be the Chern class of E1 direct sum E2. So this is the same as the second property that we wanted, that you can just see. If I multiply these, you are going to end up with exactly this type of an equation. So this shows existence. So we are done with existence and uniqueness. So now we are sort of going to mimic this. So let me just say what we are going to do next. So we want to, so first it is clear that we have to focus on Chern classes of line bundles in the beginning. So we have to understand that clearly, and then using splitting principle, and then we'll have to have some construction. So unfortunately this calculation of cohomology of projective bundle will come later. So first we will see some different construction, but that doesn't matter because we will still have splitting principle, and then we will show that it satisfies the properties that we want. So that is the plan. So next lecture will be about Chern classes of vector bundles. There are two differences actually. So in the treatment that we will see for varieties. So the first is that we have Chow groups as homology right now, and Chern classes, therefore they will not be classes in these Chow groups, but they will be sort of operators on this homology. So that is a difference that I will highlight tomorrow. So yeah, that is the first difference. Second difference is that vector bundles do not necessarily, the short exact sequence of vector bundles does not necessarily split in algebraic geometry, and therefore we'll just have to modify this this requirement to saying that for any short exact sequence of vector bundles, the total Chern class of the middle one is the product of the Chern classes of the first and the last. So these are the two minor changes we have to do. Of course, when Chow intersection product is constructed on Chow groups, then actually we will have elements, Chern classes as elements in the Chow group. So later on. So any questions? So this is more or less what I wanted to say today.
Expression to define this CI with alternate signs. Some issue with signs sometimes. You take a line. So these are line.
Oh yeah, I think signs are needed. -1 to the power I. Yes. Yeah, so maybe this this expression defining Chern classes, so if you actually try to so the problem is that this Chern class will not agree with line bundles. It will be minus of that Chern line bundle, and therefore C2 will be -1 to the power 2 and so on. In order to rectify that, I have to just raise this to the power n-1 and sorry plus -1 to the power n, or first one is the -1. Yeah, so this is -1 and this is -1 to the power n. Yes, correct. n-1. If this is -1, this cannot be n, no?
So the power of x is 0.
So -1, the power of -1 has to be the power of x.
Index of the Chern class, not the power of x. Index of the Chern class.
Okay. Yeah, so that this is correct. So that, yeah, sorry, I missed this minus sign. So yeah, so that is it.